MBSE, Model-Based Systems Engineering tutorial from Tonex training experts. Topics: in this presentation you will learn about Introduction to MBSE, MBSE Definition, System Definition, System Design Properties, the System Language, Systems Engineering Definition, Multidisciplinary Approach, Problem Classes, Top-down engineering problems, middle-out engineering problems, reverse engineering problems, the design space, 3 systems, the design space, boundaries, the process, domains, model definition, model components, successful model characteristics, language behavior characteristics, structure. The model expresses system relationships. Requirements for a systems engineering process. MBSE tools. MBSE tutorial arranged by Tonex plans to survey the idea, devices, models, and necessities of model-based systems engineering. This tutorial is a general rule to acquaint you with the themes ongoing around there and to give you a few insights on what to search for, to ponder and learn on the off chance that you have to profoundly comprehend this subject. Introduction to MBSE. The thought behind MBSE was to build up a device to streamline the comprehension of complex systems by modeling them. Indeed, MBSE encourages the system prerequisites, outline, examination, confirmation, and approval exercises. It can be utilized at any level of the system, from the starting outline, through advancement, and to life cycle stages. At the end of the day, MBSE plans to supplant the report-based techniques to enhance the act of systems engineering by completely understanding the meaning of systems engineering conventions. MBSE Definition. Model-Based Systems Engineering, MBSE, is essentially a manner of thinking. It conveys the structure to empower the systems engineering group to be productive and lucid the distance from the beginning of any undertaking to the end. In the meantime, it is enough versatile to let the thought procedure to acclimate to specific confinements or conditions existing in the issue. System Definition. As indicated by INCOS, system is built or gathered of different components that together can create the results that are not achievable by the individual components alone. Besides, a system ought to interface its parts together through conclusive connections, in a way that they are reasonably composed. System Design Properties. Entities. The parts construct a system, including atoms or molecules, larger bodies of matter like sand grains, raindrops, plants, or animals, or even components like motors, planes, missiles, etc. Attributes. The features of the entities that could be seen and evaluated, such as quantity, size, color, volume, temperature, reliability, maintainability, and mass. Relationships. The relations that happen among entities and attributes. Such relations are based on cause and effect. The system language. In order to describe a design, like any other matter, engineers need to use some form of language. Such language is defined based on the system properties, the entities, attributes, and relationships. The system language is crucial to explain and communicate the system properties and characteristics between the engineering team as well as to other stakeholders. Thanks to system language, each system can be demonstrated hierarchically, enabling it to be seen as decomposable into eloquent subunits. These subunits are traditionally named. A system is made of subsystems. Subsystems in order are comprised of assemblies. Assemblies are constituted of subassemblies, and subassemblies are combined of parts. The parts of a system communicate with each other to generate the function of the entire system. It is automatically clear that all elements of the system must be operating as planned in order for the system to operate accurately. However, it is not so clear that how enhancing the operation of one of the system elements would essentially enhance the performance of the entire system. Systems Engineering Definition. As indicated by INCOS, systems engineering is dependable to create and play out across practical technique to guarantee that the customer and partner's requests are satisfied at an abnormal state, solid, cost-effective and timetable good conduct over the entire life cycle of a system. Multidisciplinary approach. The regularity of systems engineering unites divisions of engineering and science to plan and create solutions for the stakeholders' demands. By applying a systems view of the problem and the potential solutions, systems engineers can tie the diverse disciplines to design a solution that answers the needs of the stakeholders in the most efficient way. The control of systems engineering comes from applying such cross-functional technique of problem-solving to fulfill the needs of stakeholders by creating or modifying a system. Problem classes. Top-down or clean sheet problems. Middle-out or system improvement problems. Reverse engineering or system replacement problems. Top-down engineering problems. In these situations, which are by the way the most famous one among the three problem classes, the engineering team deals with designing an exceptional system solution to stakeholder problems. Such designs are also usually called greenfield or clean sheet development works. Middle-out engineering problems. Middle-out engineering starts with modeling the as-is stage of all or a part of a system. This offers a comprehension of the current solution and the supporting procedures and technology. Reverse engineering problems. Bottom-up or reverse engineering employed to promote or substitute legacy systems, which may have been in operation for many years. Such systems could have had broad improvements and corrections added over the life of the system. These are commonly executed in the absence of sufficient documentation. If documentation is adequately available, it usually includes various losses and errors. The design space, three systems. Every system design or improvement happens within the three systems. The most noticeable is the system being designed. The system being designed will operate within a larger system. The second system is a contextual system, the system under design, living and working. The third and final system is the system that is used to design the system and make it alive. The design space, boundaries. Once the systems engineer digests the notion of the three systems, they must understand the boundary between the system being designed and the system it will live in. The first one is inside the control of the design process, and the other simply exists and must be adapted to. The process. Systems engineer firstly need to generate an unambiguous problem statement, establishing the issue or issues are being addressed by the proposed system. This requires collaborating with others, particularly system stakeholders and subject matter experts, to determine the expressed requirements that control what would describe a satisfactory solution. Domains. The work on the design progresses in four domains. Requirements. Functional behavior. Architecture. Verification and validation. Model definition. Models connect the concept behind the design solution with its execution as an actual system. Models intend to demonstrate the entities of the engineering problem, opportunities, and their interactions to each other and tie them to the projected solution or the current mechanism that describes the problem. The model used in this way is the centerpiece of MBSE. Model components. Language. Structure. Argumentation. Presentation. Successful model characteristics. Order. Power to demonstrate and persuade. Integrity and consistency. Insight. Language behavior characteristics. The capability to seize the process flow and control. The capability to seize observables. Understandability. Executability. The capability to reserve behavior across. Decomposition. Aggregation. Allocation. Structure. The model expresses system relationships. Sequence. Concurrency, or and, construct. Select, or, construct. Multiple exit function. Iterate, IT. Loop, LP. Loop exit. Replicate. Exit. Requirements for a systems engineering process. Below are the systems engineering requirements that MBSE can perfectly fulfill. The process must coherently lead to successful systems development. The process must regulate and monitor system complexity well. The process must lead to efficient solutions to a variety of customer needs. The process must be able to serve the three main problem classes: MBSE tools, functional flow and improved functional flows, and 2. IDEF0, physical block, systems engineering solutions, robust and agile analysis, requirements definition through architecture to systems verification, end-to-end traceability, extensive behavioral modeling representing control flow, function flow, and interface flow, system simulations, behavioral models, integrated model-based operational and system architecture. How can you learn more? Browse through our hands-on training courses to find what serves you best. Advanced SysML Training, Creating SysML Models, MBSE Training Crash Course, MBSE Training, Model-Based Systems Engineering Training, Model-Based Requirements Engineering, Requirements Engineering Workshop with Use Cases, SysML Training Crash Course, SysML Training, Systems Modeling Language Training. Request more information about MBSE tutorial. Visit Tonex website, links below.
You about to feel this.